Today, I'm going to tell you guys about a theorem of Miyazawa from last year. I'm going to run through the proof of his result, and it's going to be a nice culmination of all the tools and things we've learned so far throughout the last 4 lectures. Okay, so we have the following statement. So first, maybe let me do some setup. So I'm going to let P plus denotes the following embedding of RP2 into S4. All right, so this is a non-orientable 2-knot, and one description of this is it's given by the image of certain involution on CP2 bar. All right, so P plus is equal to the image of RP2 under the involution on CP2 bar given by complex conjugation. All right, and the reason for the notation plus is that this, the normal Euler number of P plus is equal to positive 2, right? And if I took away these bars then and did complex conjugation on CP2, I would get something with Euler number negative 2. Okay? Then the statement is that there exists an infinite family of embeddings of RP2, P sub n from n equals 0 to infinity, S4, such that P0 is equal to P plus over here, the standard one, and then for any two m and n, Pm is topologically isotopic to Pn, but is not smoothly isotopic to Pn. Sorry?
So we were supposed to land in the S4, right? Like when you construct this P4. So how do we go from CP2 to S4?
Under the involution, so it's quotient, sorry. Quotient, sorry. Yeah, yeah, totally valid, so. Yeah, other questions? Okay, great. And then I think just as a nice little corollary, so I guess this is like, technically the theorem that we see here plus work of Hughes, Kim, Miller implies that there exists infinitely many exotic involutions on CP2 bar, or CP2 if I reverse the orientation. Yeah. They are all given by connected sums with an orientable 2-knot from each other, yeah. They're all related by that operation. Other questions? I have no idea. Sorry. Great question, yeah. So I will tell you what all of these knots are. I'm going to explicitly construct them. But before then, let me give kind of the real Seiberg-Witten input that we're going to need for the proof of this theorem. And we're going to define a bunch of invariants. We're going to extract numbers from four manifolds and three manifolds coming from the real Seiberg-Witten construction. So the first thing I'm going to define is in the situation where we have a closed four manifold and we have an involution and a real spin C structure as defined by Hokuto. So I'm not assuming spin anymore. It could be spin C. And so as I mentioned before, in this case, we only have a Z2 action and not a Z4 action on everything. So we get an associated Bauer-Fruta map. And this is after taking fixed points under that involution, capital I, constructed from this involution. And so this is going to be a map between two spaces, and I'm going to write it like this. So the domain is going to be given as follows. So let me write it out, and then I'll explain the terms. All right, great. So we're working with Z2 actions, and there are only two different types of representations we have. So R denotes the trivial Z2 representation of dimension 1. R tilde denotes the sign representation of Z2, where plus or minus 1 acts by plus or minus 1. All right, so this is the sign representation. And here, right, we've seen these terms before. This is the index of the spin C Dirac operator. And here, this is what Hokuto talked about a couple lectures ago, right? So this is the part of B2 plus, which is fixed by minus tau. Or equivalently, it's the stuff that is not fixed by the action of tau, right? There's a complete splitting. So it's like the non-tau invariant part of B2 plus. Great, okay, so this is our map. And just as a big caveat, right, and this is really important, this is well defined, this entire map is well defined only up to sign. All right. And this is just a part of this setup, and this leads to the statement. I won't go into it too much, but essentially it has to do with the fact that if you try to apply Kuper's theorem about real Hilbert bundles and try to trivialize them, well, there's kind of like two components of ON, and so there's no canonical trivialization. And so we only get a map that's defined up to sign. But it's like kind of like in the weeds somewhere where we get this sign ambiguity. Great. So, okay, so we have that map over there, and then let me make an assumption. All right, so this is not always going to be true, but suppose we are in the special case where that number appearing there, C1 squared S minus sigma x over 8, is equal to B plus negative tau x. All right. Well, in that case, both of the dimensions of those two vector spaces are exactly equal. All right, and if I forget about the Z2 action floating around, so let me just think about this non-equivariantly. this Bauer-Fruta invariant. So I'm going to put a little e over here. And this means that I'm like restricting to the action of the trivial group on here. So I'm forgetting the equivariance. All right, this is a map between two spheres of the same dimension. And stably, right, this is an element of this, pi 0 stable of S0. Great. That's a very nice, well understood group. Right, and then so we have a map given by the degree of that map between spheres to Z. Now, there's an issue here, right? That map is only well defined up to sign, right? So actually, what I really get is a map to pi 0 stable, but really mod plus or minus 1, right? Because of that sign ambiguity. And so the target here is Z mod plus or minus 1. Sorry. Great. So what I can do instead is I have a well-defined map where I can take the absolute value of the degree of my map between spheres, and that thing is well-defined even modulo that sign ambiguity. All right, so I get a map from here to here, and then kind of like, this is maybe bad notation, but I'll just think about it as I'll just take the positive part. So maybe I'll like identify this with non-negative integers, right? And here I'm implicitly doing that by taking the absolute value. All right, and then so then I will define this invariant, the absolute value of the degree of this triple x s tau as like the absolute value of the degree of this Bauer-Fruta map. Sorry. As a non-negative energy. Sorry, are there any questions? Great, so it's a rather simple invariant. I just, if I'm in the case where it's a map between two spheres of the same dimension, I just take the degree as a map between spheres and then take the absolute value. Great, so that's for closed form manifolds. For manifolds with boundary, I can do a similar thing under some assumptions. Right, so let's xs tau, this is a 4 manifold, but it has boundary now. So with boundary, I'll just write, its boundary is y, and then like the restriction of real spin C structure is t, and iota for the restriction of tau. Okay, so again, we get a very similar type of map. We get this relative Bauer-Fruta map, relative real Bauer-Fruta map. And everything looks kind of similar, except we get an extra term. Right, so this goes from r tilde, save expression C1 squared minus sigma x over 8 plus to r to the b plus negative tau of x. And then, right, for the relative Bauer-Fruta map, we get an extra term. We get a smash product with the real Seiberg-Witten Floer spectrum of the boundary of YSI iota. Great. So how do we rig up a similar map? Well, I can do that if I make some assumptions again, right? So if we assume the following, so I'm going to assume two things. Actually, let me. Yes, thank you. All right, so if we assume the following, so I'm just going to assume this guy is a sphere. All right, so assume that the floor stable homotopy type of YS iota is homotopy equivalent to 1-point compactification of some vector space V. V is like Z2 vector space. All right, and then suppose, now what I'm going to do, I'm going to assume that almost the same thing as before, C1s squared minus sigma x over 8 is equal to b plus minus tau of x plus the real dimension of v. Yeah. Oh, sorry. Yeah, Z2 equivariant real vector space. Thank you. Yeah, yeah. Yeah, that would be weird. Yeah. Iota is the restriction of tau. Kind of like this tuple is like the boundary of this tuple. Okay, great. So under these two assumptions, well, what's going on? Well, this is just some sphere. I'm forgetting the equivariance now. So like I have sphere, 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 and then the dimension here adds up, is equal to the dimension of these two. And so again, non-equivariantly, I get a map between two spheres of the same dimension. All right, so, all right. And then again, I can define absolute value of the degree, which lands in non-negative integers. Okay, so I won't write it down, but yeah, then we define the absolute value of degree of this thing to be that, the degree of that map over there, as before. And then also, I'd like to point out that these invariants are multiplicative under gluing in the following sense. So if I have, let's say, x and x prime glued along their common boundaries, and then, I'll write it like this, s union s prime, tau union tau prime, take the degree of that invariant, then this is equal to degree of x s tau times degree of x prime s prime tau prime. And so this formula holds precisely when all three of these guys are defined, right? So remember, I made a bunch of assumptions for the closed case in the case with boundary, and so this holds when these guys actually make sense. Okay, so I will say the proof of this is actually very hard and maybe somewhat standard these days, but gluing arguments in Bauer-Fruta theory are a little tedious. And technical, but nothing, too novel appears here, I would say. All right, and then I'm going to define a third invariant specifically for three manifolds with an involution. All right, so now we have Y3, some real spin C structure, and some involution iota. And this one's going to be defined a little differently. So I'm actually able to define it not just for, if the floor spectrum is a sphere. I'm going to do the following thing. All right, so the degree of this tuple, or absolute value of degree, I want to define it as follows. All right, hopefully I can fit it here. Maybe I'll put it over here. Okay, so I have the real Seiberg-Witten floor stable homotopy type of this tuple, yt iota. And then I can take reduced non-equivariant cohomology. All right, this is Z2 equivariant, but I'm going to only take the non-equivariant homology. And then, okay, I'm going to take the Euler characteristic of this homology, meaning just the alternating sum of Betti numbers in the usual sense. And then I'm going to take the absolute value of that Euler characteristic. Okay. So this lands in z greater than or equal to 0. And kind of what's nice when you take the absolute value of the Euler characteristic is like grading shifts kind of like don't affect anything just because, yeah, great. So just as like a kind of like motivation and maybe like comparing this to other things that you've seen before, in the usual case, right, the non-equivariant homology of the floor spectrum is isomorphic to HM tilde, which is isomorphic to HF hat of the three-manifold, right? And so you should think about this invariant as like an analog of the Euler characteristic of HF hat. And those two maps that I defined before, those Bauer-Fruta maps, they're kind of like the cobordism maps on HF hat. Now, in the non-equivariant setting, those maps are very boring, right? The Euler characteristic of HF hat is boring. Same with the cobordism maps. But if we restrict to this like I fixed set, then these maps become very interesting. All right, so that's something kind of like a salient point that I wanted to make. All right, so good. Any questions so far? All right, great. How much time do I have left? Oh, right. Okay, so I'm going to find two invariants of two knots. Jesus, okay. Let S be a map from S2 into S4. Define invariant. I'll call it absolute value degree of S. And what I'm going to do is I'm going to define it to be the absolute value of the degree of the double branched cover. Right? So if I take the double branched cover of this 2 knot, well, this is going to be some Z2 homology S4, and it has a covering involution given by here, and then some, because it's a Z2 homology guy, there's a unique spin structure, unique real spin structure on there. All right, and then I can also define an invariant for P2 knots. So, let P be an embedding of RP2 into S4 with P, topologically isotopic to that P plus that we said before. So, like normal Euler number 2. And then we're going to make an assumption just to make our lives easier. So we're going to assume that the double branch cover of P is a integer homology CP2 bar. All right, so you can check that it's always going to be a Z2 homology CP2 bar, but I'm just going to assume this for the sake of this, just so I don't have to care too much about the spin C structures floating around. So this one's a little more interesting to define. So I'm going to define the absolute value of degree of P to be equal to the absolute value of the degree of double branch cover with a certain spin structure, real spin C structure, and the covering involution, tau, I guess. However, in this setup, well, the double branch cover, all right, is not gonna be spin, right? If P is equal to P plus, right, the double branch cover is CP2 bar. And so, in fact, this guy is a real spin C structure, which is not a real spin structure. And we actually have that S is equal to the unique real spin C structure such that C1S squared is equal to -1. All right, why did I pick -1? Well, maybe, exercise check that this guy makes this well-defined, right? Remember, I needed some assumption on those kind of like two quantities that were appearing. Great. All right, so cool. And then some nice facts about these. So they satisfy the following properties. If I have two knots, then it's additive under connected sums, or multiplicative, sorry. Very different. So, sorry. Degree of S1 connects some S2 is degree of S1 times degree of S2. We also have a funny thing. If I take a P2 knot and then connect some with a 2 knot, then this is also multiplicative. So absolute value of degree of P times the absolute value of degree of S. Yeah. Yeah, yeah, yes. Yeah.
It like matches the P.
Yep, exactly. Yeah. Or the invariant B plus, yeah. Or non-invariant B plus. All right, and then the last thing is that the degree of like the standard P2 knot P plus is equal to 1. All right, so with the time remaining, I'll try to, outline at least the construction of these guys. So let me tell you what this family is. Remember those Pn that appeared in there. It turns out that these Pn are given by the following. So we have P plus connected sum with n copies of what is called the zero-twisted, once-rolled spun knot of P minus 237. Okay, I'll explain what this notation means and how to construct these. So these are two knots, like embeddings of S2 into S4. All right, so what is a twist spun roll knot? Let's pick my favorite knot, K and S3. That's my favorite knot, maybe, I don't know. Let me scoop out a neighborhood of a point on the knot. All right, and so I'll get like a corresponding 1-1 tangle inside of B3, denoted by K bar. So here it is. Yeah, I think that's right. Okay. Cool, so great, so given such a knot, and I guess the K bar, so let me define this two knots, tau m rho n k, m twist n roll spin of k. These are two integers. All right, so we're going to build this in 3 pieces, kind of. So we're going to build, the pair S4 comma tau m rho n of k, in 3 parts. So kind of the first part is the most interesting maybe, so I'll try my best to draw the following. Boy. Yeah. Okay, great. So what I've taken is the exterior of K bar inside of B3. So I chopped out a tubular neighborhood. And then what I'm going to do is take a mapping torus of a certain diffeomorphism. So I'm going to define X, comma, this is the empty set. So we first start off with no surface. So as pairs, this is the exterior of K bar. I'm going to write it this way, just for shorthand. This is the mapping torus with respect to a certain involution, phi mn S1. So I'm kind of like thinking about it as like a twisted bundle over S1. All right. Comma, empty set. So let me define this phi mn. Great. So good. So X is this guy. So let me let T be equal to the boundary of EK bar, but pushed in. All right, so this is homeomorphic to a torus. And I'm going to make an identification of the closure of a tubular neighborhood of T with T2 cross I. And then basically I'm going to define a diffeomorphism like on the neighborhood of this torus, and then it's going to be the identity everywhere else. All right, so we got CMN goes from T2 cross I to itself, and I'll let theta and C be my 2 circle coordinates on T2. And it goes the following. Actually, I should fix a basis first, otherwise this is kind of meaningless. Okay, so I fix a basis here. So imagine T is like a pushed-in boundary of this guy. And there's kind of like a canonical choice of basis here. We have the meridian. And then the longitude is going to kind of like go through, like wrap around the knot, and then like come back and then like swing around and be on the boundary of this 3 ball. So that's lambda. And so mu, lambda, and that's my 2 coordinates. Okay, great. So this diffeomorphism, what it does is as I go through the kind of like time direction, it's rotating around by m and n in the first and second coordinates. This is completely wrong, sorry. There you go. M and then n, great. Yeah, thank you. Right, and then I'll just define that phi as, CMN on boundary, or yeah, that tubular neighborhood of T, and then identity otherwise. Great, so that's that diffeomorphism that I am taking the mapping torus of to define X. All right, so for the sake of time, I will just say that in order to finish this off, we have to glue on 2 kind of auxiliary pieces. So I'll just say it out loud. First off, we're going to glue in a copy of D2 cross I cross S1 to fill in the neighborhood of this knot that I scooped out. All right, so I'll just fill that in. And then what are we left with after we fill this in? Well, on the boundary is just going to be a copy of D3 cross S1. And then I can just glue in an S2 cross D2 at the end. All right. Instead of working with all of that, it turns out what I can do is the following. The boundary of this guy, after I like smooth corners, can be identified with T3. And I'll just say there's a canonical sort of pair, Z4 and S, with the boundary of Z4 is homeomorphic to T3, and then S is an embedded two-sphere. And this spun knot tau m rho n k is just the union of x comma the empty set along their common boundary with z comma s. All right. Sorry, I'm going to have to erase this fun picture. All right, so I'll say a little bit, right? So how do we build the double branch cover of this two knot? Well, under this kind of like construction that I did, it's actually like not too tricky, right? So like basically what's going to happen is that when I take the double branch cover, it kind of like respects this decomposition, x and z, and like it's just going to be the regular twofold cover of x, and then like a standard double branch cover of z. All right, so this is regular double cover of x, you know, corresponding to like pi 1 of x z mod 2 that sends the meridian to 1. Okay.
So we constructed X, but we say that Z exists?
Yeah, the z exists, but I mean, I was going to construct it, but I can't. So, so what is the upshot here? You know, the double branch cover of this two knot is equal to x tilde union along the boundary of, okay, the double branch cover of the other piece over that sphere sitting inside of it. But the point is that double branch cover of Z is actually homeomorphic to Z itself. All right, so you know, I didn't get a draw picture, but the Z is made up of two pieces. Kind of there's like a D2 cross I cross S1, and it's kind of like unfolded in like a direction where you get the same thing back, kind of like the double branch cover of a solid torus over a core circle. And a similar description for the other piece. Okay. Great. And then maybe what do we really need? Kind of, the double branch cover of this 2-knot, right? Okay, I have an identification with x tilde union z. And if I instead of gluing on this z, I glued on a copy of d2 cross t2 in a certain way, then I would recover not the double branch cover of this guy, but in fact just the double branch cover of k cross S1. So you can think about these as being related by kind of surgery along a loop inside of Z. Great. Cool. So let's make some assumptions. So suppose that the determinant of my knot is equal to 1. In which case the double branch cover of K is an integer homology 3-sphere. It'll just make our lives easier so that unique real spin structures popping up. And then also I'm going to make the assumption that m over 2 plus n is odd. And the reason I'm doing this is kind of, there exists a real spin C structure, or actually spin structure S, which extends to both of these. All right, so let me just put all of the pieces together. So I'm just going to list a series of facts. So we have kind of like the T3 boundary, which like these guys are being glued along. So one fact is the real Seiberg-Witten stable floor homotopy type is of this T3 is actually stable homotopy equivalent to S0 is trivial. This is not true for a regular 3-torus. Like the floor homology of a 3-torus is very interesting, usually. But with the induced involution on this 3-torus that we are considering under this double branch cover construction, turns out that the real floor homotopy type of that guy is trivial. Good. Secondly, the degree invariant of both those pieces, Z and degree of D2 times T2, and I'm suppressing spin structures and involutions, but they are lurking around the background. They're both equal to 1. And then finally, the degree invariance of the double branch cover of K times S1 is equal to the absolute value of the degree invariant of the double branch cover of K. No. Thanks. Yeah, what's up? That's a T. That's a spin structure. Okay, so this is as an invariant of a 4-manifold, right? Degree of map between spheres, and this is the invariant of the 3-manifold, is that Euler characteristic. Great, so, you know, the first two aren't hard to show, and the third one is kind of like a standard thing that happens in Seiberg-Witten theory, like kind of the you know, solutions on 3 manifolds, you kind of like pull them back up to sigma 2 cross S1, and somehow like all the solutions on this manifold are ones that came from ones downstairs. All right, so corollary. Great, if you put all of the facts together, I'll leave as an exercise if you were, you know, taking careful notes. All of these together imply that the degree of the double branch cover of the 2-knot is precisely equal to the degree invariant of the double branch cover of K as like a 3-manifold. Okay, so exercise. Good. M over 2 plus n is odd. And m is even for us to take a double branch cover in the first place of that knot. So that's important. But that works. Both of those things hold for what we had. Great. So good. All right. Now let's look at the case where we have tau 0 rho 1 of the knots, the pretzel knots p minus 2, 3, 7. All right, so now we're specializing. All right. So good. So maybe I'll just write down the steps. You can check. So proof of main theorem. I'm sorry for going over time, but I promise I'm almost done. So Pn was that family of knots I wrote before. It's P plus connected some n copies of the 2 knot I wrote on the board before. And by this corollary, this is equal to the degree invariant of what? Well, of double branch cover of n copies of the p minus 2, 3, 7 pretzel knot. And then by multiplicativity of the invariant, right, this is equal to n times the degree invariant of sigma 2, 3, 7, right? And here implicitly, I dropped all the subscripts here, but what is the covering involution of this? Well, it turns out that the double branch cover of this guy is sigma 2, 3, 7, and the covering involution is that complex conjugation involution that I introduced yesterday. Great, and then so calculated the floor spectrum of this guy last time, right? So this was the following. So I desuspended by 1/2 copies of that vector space V. And this was the unreduced suspension of Z mod 4. Okay? So what did this guy look like? This was that 4-strand bird cage that I drew last time. It looks like this, but they're not bananas. They're just 4 strands, top and bottom. Great. Well, non-equivariantly, I could take this kind of top point where they're all joined together and kind of like move it down below, and then actually, you can squint a little bit, this is actually homotopy equivalent to the wedge of 3 circles, non-equivariantly. All right, and so non-equivariantly, this is homotopy equivalent to the one-fold desuspension of wedge of 3 circles. All right, and then I can just commute with over there. And so this is the 3-fold wedge of S0, or if you like, it's just this. Okay, well, what is the Euler characteristic of the homology of that guy? I mean, well, this is rank 3 in 1 degree, so the Euler characteristic is 3. After I take the absolute value, it's definitely 3. Okay, great. And then so putting this all together, this is equal to 3n. And so all of these guys have different degree invariants, and so they are not smoothly isotopic. All right, those are invariants of P2 knots. However, one can check that their fundamental groups of their complements are all isomorphic to Z mod 2. And so by result by Conway, Orson, Powell, they were all topologically isotopic in S4, and so hence our exotic family. All right, why don't we end there? All right, great. So yeah, sorry I went a little over time. Maybe I'll take like one question, but then. Yeah, what's up?
What was the significance of this pretzel knot?
Great, yeah. So the significance of this pretzel knot, well, one is that like this Floer spectrum was like interesting enough to have Euler characters like not equal to 1. But the other thing that's really important is the fact that these are all topologically isotopic to that P+. Right, this is not going to be true for a generic guy, right? Like I do a fundamental group calculation and they could just be like, you know, they'll all be alienized to Z2, but not be exactly Z2. So this is like something special about the fundamental group of this knot, kind of. All right, great. Well, yeah, why don't we end there?